You've been doing this already. In chapter 2, we started with finding the slope of a curve at a particular point and how to measure the rate at which it is. And then you found a tangent line to the graph of a function. You had a particular point, and then what you did is you found a point nearby, and we just kind of said then you cancel things out and you let things go 0. So this is what you've been doing. We're just adding this piece now because hopefully you know what a limit is. Haha, that's a joke. Do you know what a limit is? Yeah. So you've been doing this piece, and then we'd just cancel and we'd say, well, set h to 0. But the reason why is we're taking the limit to this function as h is getting smaller and smaller and smaller. So it's doing the same thing where you have the secant line and then finally get to one point where you have a tangent line. So this is kind of nice because 3.1 and even 3.2, there's not really anything new. Okay, so it's a good. All right, so if I want to find the slope of a curve at any point, like let's say at y equals 1 over x at the point x equals a, which of course cannot equal 0. So all we're saying here is at any point. That says any somehow. Says any. All right, so we use this same thing that we've been doing, the limit as h goes to 0, but we're saying at any point. So we're calling our XA. That just means I can pick any value for that point, and now I'm going to just take this and plug into my actual function. So again, this shouldn't look like anything new or different to you, meaning that the limit as h goes to 0 of 1 over a plus h minus 1 over a all over h. All I did was plug in a plus h and then plug in a. And now, remember that what you're doing here is you're trying to get it to a point where you can plug in h equals 0. You can't, so you have to do some things. Most of you call this, which is fine, cross multiplying. So I'm getting a common denominator. And so I'm going to have the limit as h goes to 0 of a minus a plus h all over a times a plus h all over h. So all I did on the, why is that like lower? All I did was on the bottom here is just multiply that out. And again, we're going to just carry, whenever you have denominators that are kind of complicated, you just carry them every step along the way. So this is going to equal the limit as h goes to 0. Certainly, you can see that cancels. I end up with a negative h on the top. I'm going to bring all that down to the bottom. So this is a plus h. That cancels. So I end up with the limit as h goes to 0 of negative 1 over a plus a times h. A plus a times h, I don't know what I just said, a times a plus h. And so now I'm to the point I can plug in 0. So again, I hope you go, well, we've done this already. We did, but we didn't formally say you could do this. We just got down to this step and said just plug in 0 for h, but now we're actually finding the limit. And so in this case, I'm going to have negative 1 over a squared. And so what we're finding, instead of a number, the slope, we are actually finding a function. So we started with a function, and we ended up with another function. Okay, so the difference is here now we're going to say, well, I want to know any value that I can plug in. So if I want to look at something, come on, you can do it. If I want to look at something, so I just found this was my function, and now I say, well, what is the slope at x equals negative 1? Well, remember my a was for any x, so I just simply plug in that value that I'm looking for. And what this tells me is if I'm looking at my original graph of my function, then I know how that function is changing at that particular time, if we're talking of time. If I wanted to find something like, where does the slope equal -1/4, maybe you want to know for a function when it's starting to decrease, okay, the rate of change is decreasing, we'll simply plug in, use this same, we're saying that this is the formula for the slope, so I'm going to have -1/a² equals -1/4. Solving this for a, meaning I'm just going to kind of move things to each other side, so I'm going to have 4 equals a². I know we get out of the habit of this, but you should be doing plus or minus when you're taking square roots. And so we get plus or minus 2 equals a. So again, what does this mean? Well, if I'm at the point -2, -1/2, and the point 2 1/2, okay, I'm saying that that's what the slope is at those points. Of course, where did I get -1/2 and 1/2? I just simply plugged in -2 and 2. I got my y values. These are my x, y values. So at those 2 points, the slope is -1/4. All right, so what we started with all this, and this is what it's called in your pre-cal book. If you went back and looked in your pre-cal book, they call it the difference quotient. It's just one little section, and I always tell my students, remember this, you're going to see it again in calculus. Do they remember it? No, because it's just one small section in there. But so we started out with the, and when we added that limit piece out front here, okay, as we're letting h go to 0, this piece right here was just the average rate of change. When we added the limit piece, that became the instantaneous rate of change, which is the definition of a derivative. Okay, so our derivative, if we want to come up with an actual function and say we plug in any value, this is one way, you'll see some other ways here in a minute, how the derivative's typically written, this f prime at this particular x value. So we're saying at that point, what is the derivative? What is a derivative? Well, it's the limit of this function. What is the limit of this function? The slope. Okay, so that's all you're doing is you're finding slopes. So this difference quotient, again, was the average rate of change. The derivative, when I add that limit piece, that becomes the instantaneous rate of change. So that's all we're doing is making this go to 0, okay, so we can get closer and closer and closer to that point, and that gives us. Well, we can't, but that's what we did, right, in 2.1, is we canceled things out so we could plug in 0. But now we're actually saying as the function gets close to 0, in this case, our function, this, just happens to be the slope. So you're doing the same thing, we're just saying the concept's different because you didn't really know in 2.1 what a limit was. You were just doing it, we just didn't tell you you were doing it, basically, yeah. And so this is for, all of these mean the same things. In other words, on a test, you might be asked to find the slope of the graph at a particular point. You might ask to find the tangent line, okay, at that point. You may be asked to find the rate of change, or you may be asked to find the derivative. Okay, so it may not say find the derivative at x equals 1 for this particular function. It may say the rate of change, of something that's moving. So you just have to be familiar with all these definitions of the derivative. All right, now back in when we first did this, we looked at our formula and we said, well, that's just simply finding the slope, and we did something like y equals 3x plus 5. When you went through the whole definition, you ended up with 3x as your slope. Well, now let's just say that for any linear function, if I have mx plus b, so this is just going to be a proof that if I'm now at any point, because of course a linear function, the slope is constant, it's going to be the same no matter where you are, then if I'm at this point x naught and my y is m x naught plus b. So there's my actual point. Well, then I can take the limit of this, meaning m times my x naught plus h, because I'm still letting h go to 0, plus b. So that's my first piece. My second piece is where I plug in just the x naught. So I'm using the linear function. I'm just saying for any value of x now. And then, as you can see, if you multiply or distribute this out, you get m x naught plus m h plus b minus m x naught minus b all over h. That cancels, and so now you're left simply with the limit as h goes to 0 of mh over h, which is the definition of the slope. So what this is just a proof that doesn't matter any value. If you have a linear function, any place you pick an x value, I can prove that this definition here gives me the actual slope. All right, so an application at t seconds after liftoff, the height of a rocket is 3t. How fast is the rocket climbing 10 seconds after liftoff? Perfect example. Nothing here said find the derivative, okay? So you have to get where you recognize these. You know, right now is not bad because we don't have that much material, but come the final exam, when you just have a question like this, you're going to have to interpret this, oh, they just want me to find the derivative at exactly 10 seconds. So that's what they're asking me to change. So I start out with my function, okay? I just use t for seconds now, or for time. Now, a lot of students will say, can I just work this out with t's in there, and at the very end plug in 10? That's actually a better way to do it, because what you've done is you've come up with a derivative function that now you can plug in any value, 10 seconds, 9 seconds, 12 seconds. But starting this out and plug in everywhere I see a t, I'm going to plug in 10. And now this is my function. So my function plugging in these values. Okay, again, like I said, this should be very good review for Chapter 2. You're going to have problems just like this on the test. I mean, the difference is until we got towards the end of Chapter 2, you really didn't know what a limit was, but this is what you were doing all along when we just said let h equal 0. So now the rest of this is where I square this piece out, then I'm going to these, and as I've mentioned over and over and over, does not happen, then something is wrong. You need to back up here, because you should only end up with h's, or if you left some t's in here, then those would cancel out as well, because your t values are going to end up being numbers, okay, whatever you're plugging in. So now my is to simply factor out and then finally limit of the constant, and I get my answer. Okay, so therefore the rocket is climbing at a rate of 60 feet per second at exactly 10 seconds, and that's what this definition says, at exactly 10 seconds. If I wanted to find the average rate, then I may be looking, say, from 10 to 11 seconds. Okay, but in this case, I'm looking at exactly this. So that's the whole point of letting this go to 0, is I'm finding my average rate of change as close as I can to 10 seconds. And that is 3.1. So there shouldn't be really anything new